let's start today's lecture. So we are going to continue our discussion on the eigenvalues and eigenvectors. So last time what we saw is we saw how to find the eigenvalues and eigenvectors when we have repeated eigenvalues. So what we actually saw, let me actually rewrite the matrix that we actually used the last time. So our matrix was 6, 1, -2, -2, 6, 2, 0, -1, 8. And we saw that the eigenvalues for this uh, was 6, 6, and 8. And corresponding to each of these eigenvalues, there has to be one eigenvector. That's what we discussed. We need to have V1, we need to have V2, and uh, they must actually point to different directions because eigenvectors correspond to different directions. So they must be different. They must point to different directions. They should not be just like a scalar multiple of each other. So this will be more pronounced when you have a repetitive eigenvalue. So when you have repeated eigenvalue, then um, basically we may not have independent eigenvectors obtained from the simple solution of the equations that we solve. So using this equation, we used to get eigenvalues, solve this equation for eigenvectors, for eigenvectors. And what we saw that if we have different lambdas, if we have lambdas which are of different numbers or different scalar numbers, then eigenvectors would be linearly independent. Linearly independent means it will not depend on each other. So I will have a distinct eigenvector for each one of the distinct eigenvalues. But when I have same eigenvalues, then I saw that basically in that case, I may or may not get independent eigenvectors, and to get the missing eigenvectors, what we actually saw, what notation did we use last time? Let me actually look at it. Okay, V lambda. Okay, when we lambda 1. So V lambda 1 I V1 missing is equals to V1 available. So this is the equation we used in case we do not get independent eigenvector using this equation. Are you guys with me?
Yes.
Yeah.
Yeah, we saw that in the last lecture. Everybody is following it, or if you have any questions so far.
Yes.
So just there is a technical term for this. We just call as geometrical multiplicity and algebraic multiplicity. So what is this? This is called as geometric multiplicity. And this is algebraic multiplicity. What it basically means that for each lambda I, if I have repeated eigenvalues, just like for 6, I have 2 6 is basically getting repeated twice. So basically that means that corresponding to lambdas equals 6, the algebraic multiplicity is 2 because it is repeated twice. For 8, the eigenvalue of 8, algebraic multiplicity is only 1, that there is no multiple of 8, it is only one eigenvalue. But there are there is 2 multiples of 6, that means the algebraic multiplicity of eigenvalue 6 is 2. And this is geometric multiplicity means that corresponding to each one of the eigenvalues, how many distinct or independent eigenvectors I can get or I can extract using this equation. If I can extract as many uh, independent eigenvectors as the number of eigenvalues are, then geometric multiplicity will be same as algebraic multiplicity. But in case that I do not have independent eigenvector, just for this example, we saw that we only get one independent eigenvector. We cannot get 2 independent eigenvectors. So in that case, geometric multiplicity for 6 is 1, and for algebraic multiplicity is 2. That means one eigenvector is missing. And when that is missing, we use this equation to find that missing eigenvector. Is it making sense, guys, so far?
Yeah.
Any questions from anyone so far?
Professor, in
So,
that equation, the eigenvalue 1 is the one that corresponds to the 8 or to the
yeah,
6?
6, lambda 1. This is lambda 1. This is lambda 2. This is lambda 3.
Okay, thank you.
Yeah. Okay, so then we wrapped up our discussion last time with saying that you can construct a matrix Q consisting of all the eigenvectors that you have got v1, v1 missing, v1 available, and v3. So since we have three eigenvectors corresponding to this problem, so we basically have three columns, and if we arrange the eigenvectors in these three columns, we get a specific matrix Q. And we also saw that if we just use this matrix multiplication, Q inverse AQ, you actually end up with a Jordan matrix form, which is, let me rewrite it from what we saw that. It was 610 060 008, and this is called as Jordan matrix or Jordan form. Jordan form is basically, it is a block diagonal form. Block diagonal is, this is called one uh, Jordan block. This is one Jordan block corresponding to lambda equals 6, and this is basically the diagonal entry corresponding to lambda is equals to 8. So depending on what your eigenvalues are, if you do this matrix multiplication, where Q matrix is obtained by combining your eigenvectors, if you use this, you basically end up with a matrix in this form. And I also mentioned you that if I would have distinct eigenvalues, instead of repeated eigenvalues, I have distinct eigenvalues, then in that case, the eigenvectors that would I have got will be all linearly independent of each other. So there will be no such missing, everything will be available by solving this specific equation. And if I arrange it like that, where these eigenvectors correspond to distinct eigenvalues. So if I have to find the eigenvectors corresponding to distinct eigenvalues, distinct means there is no repeated eigenvalue, it is all different. So if I have different eigenvalues, real and distinct eigenvalues, then I will have linearly independent eigenvectors, and that will be uh, that combination of all the eigenvectors arranged in a matrix form. Let's call it matrix P. And if I do the same operation just like I did previously with matrix A, my matrix A will be different because it has got three different eigenvalues. So what I will get is a diagonal matrix lambda 1 0 0 0 lambda 2 0 0 0 lambda 3, where all the diagonal entries are your actual eigenvalues. So this is your diagonal matrix.
Professor,
Yes.
could you quickly explain what linearly independent means again?
Okay, linearly independent basically means that the rank of the matrix is the same as the size of the square matrix. So if it is n by n matrix, and if you construct the rank, or if you find the rank, if you, I don't know if you remember the rank discussions we had. So what we actually did, we actually try to find out using elementary row operations. We try to find it in an upper triangular form. And in the upper triangular form, if you do not have any non-zero rows, I mean, let's say for 3 by 3 matrix, if I actually use this matrix A and I do elementary row operation, I will basically end up with an upper triangular matrix. Remember that we did in Gaussian elimination?
Yeah, I remember. Okay.
Yeah. So A11, A12, A13, A22, A23, A33. So these are all zeros. So if you have a if you have a non-zero row here after performing all your elementary row operations, then you basically find the rank of the matrix. So for this, the rank of the matrix is just 3 because it is a 3 by 3 matrix and there are no zero rows. But after elementary row operations, if you end up with something like this, A11, A12, A13, 0, A21, A22, 0, 0, 0. So in that case, basically what it means that the rank of this matrix is 2. Rank of this matrix is 3 after performing elementary row operations, after EROs.
So if the rank equals the n by n number, then
Yes.
it's
If the rank basically becomes equals to n, that means it is all the rows and columns are linearly independent. They are not dependent on each other. So these columns, all columns are independent of each other, or all the rows are independent of each other. But in this scenario, what is happening? The rows are basically, one of the row is not independent, because it means that this row is basically some linear combination of the other two rows. That's why basically you are able to make it 0.
okay.
Does it make sense?
Yeah.
So when I say linearly independent, means there is no specific constant exists that this specific eigenvector is independent of any linear combination of these two vectors. Does it make sense?
Sort of. Yeah.
Another example, a quick example that help you to visualize. If I have the vectors which are perpendicular to each other, which is our coordinate system. So x, y, and z. I have 3 coordinate systems, and each one of them, let's say, represent a vector. So this represents a vector given by 1, 0, 0. This represents a vector given by 0, 1, 0, and this represents a vector given by 0, 0, 1. So what it basically means that each one of these vectors or directions are independent of the other. Are you seeing what I'm saying? That there is no way that I can extract a vector x by combining y and z vector. If I do any combination of, if I just add y and z together, I will never get 1, 0, 0. No matter whatever constants you multiply this with, you multiply this with 0, you multiply this with 0, you will end up with 0, 0, 0. You will never end up with 1, 0, 0.
Okay. So no combination of any of the other vectors
Yes,
will give you the
yes,
other vector.
yes,
Okay.
yes, exactly.
Got it.
So that basically means you are having a linearly independent.
Got it. Thank you.
Welcome. So you have got, now we were basically saying that discussion having the eigenvectors. So once we have got these eigenvectors and arrange them, so for the case is when GM, geometric multiplicity, is less than algebraic multiplicity, we call the matrix A as defective. So in that case, matrix A is called as defective matrix. Defective matrix basically means we cannot get independent eigenvectors using this specific solution. We need to use another equation to find the missing eigenvector. So when matrix A is defective, we generally get Q matrix, where we actually have one eigenvector, which is a missing eigenvector obtained from this equation. But once we get this matrix and we do this operation, we got something like this matrix, which is a block diagonal form where diagonal elements are your eigenvalues. But since it is a defective matrix, there is element 1 as well in the super diagonal. Super diagonal means above the diagonal, and subdiagonal means below the diagonal. So you have entry and one value, or one scalar number equals to 1, which appears in the super diagonal form. But if you do not have this type of missing case, if the matrix is diagonalizable, then you have distinct eigenvalues, linearly independent eigenvectors. And for these linearly independent eigenvectors, when you do this matrix multiplication, then you will end up with this specific diagonal form where each diagonal is just your eigenvalues, 3 distinct eigenvalues. Is everybody following it so far?
Quick question.
Go ahead.
So for eigenvalue 1, is there a certain range that we need to put in that? We always end up with the same diagonal matrix, or is there?
Can you speak a bit louder? I'm unable to hear you properly.
Yeah. So for the diagonal matrix, it's lambda 1, lambda 2, lambda 3.
Yeah.
If you go back to the P equal matrix, can, is there a certain order that we need to put these
No.
in?
No, it can be V3, V2, V1 because they since they are all independent of each other, you can arrange them in any way that you like. That's fine.
Okay, thank
You don't need to have, okay, I see what you are saying. So in case you arrange it V3, V2, V1, then you will have lambda 3, lambda 2, lambda. So eigenvalues will get rearranged accordingly.
you. Okay, thank you.
Yeah. So if you have lambda 1, lambda 2, lambda 3, that means it has to be V1, V2, V3. If it is 3, 1, 2, then it will be 3, 1, 2 as well. Lambda 3, lambda 1, lambda 2. The diagonal entries will basically get rearranged accordingly. Okay. Is everybody with me so far? Yeah.
Yes.
Yes.
Good. So now we are basically going to take our discussion forward and see why do we actually care about these specific form. So what we will do next is basically look at a system of second order differential equations. But let me actually, just take a textbook example. A textbook example basically has a physical system, which is a simple mass system. Let me actually also tell you which example I'm looking at this point of time. It is example 9.15. So I'm basically considering the physical system from the textbook example 9.15, where I have two mass system. M1, this is a frictionless floor, let's say. This is attached to a spring of constant K1. Then another spring is attached to another mass M2. And there is a specific force is applied at mass M1. So F is applied, external force is applied here. And to basically describe the governing equation of motion, you basically take two generalized coordinates, x1 and x2. X1 represents this basically reference represents the origin of mass m1 at time 0, and this represents the at time 0, this is mass m2 at this position, and from here wherever it is displacing, that displacement is given by x2 for mass m2, and x1 is basically measured from this reference system representing the position or the location or displacement of mass m1. So to write the equations of motion for this, if you remember that we can basically draw a free body diagram for each one of the masses. So let's basically do that. So we have M2, and if it is basically it is experiencing a force given by x2 minus x1. X2 minus x1 is the net displacement of this, and it is moving in this, assuming it is basically moving in this direction. So m2 mass times acceleration basically will be equals to the force that is being experienced, and the force is in the negative direction. So we are writing this equation as our first equation of motion. Is everybody following it so far? Is everybody with me so far?
Yes.
Yeah.
Yeah.
Yes, Professor.
Great. So for the other block, mass m1, we write the similar set of equation. So I have k2 x2 minus x1, assuming x2 is greater than x1. So basically this is displaced larger than x1. And I am basically experiencing a force F, and I'm experiencing a spring force K1 x1 in the opposite direction. So if I write the equation of motion for this, what I will get is mass times acceleration, which is double derivative, basically double derivative with respect to time. It should be equals to K2 x2 minus x1 minus K1 x1 plus F. So that is your second system of equation. So if I rearrange this equation in matrix form, what do I get? So let me rewrite the equations in matrix form. So what I will do, I will actually put all the x1 and x2 unknowns variables or displacements on the left hand side. The right hand side will be the force vector. So if I take this equation first, I will get m1 x1 double dot plus k1 x1 plus k2 x2 minus k2 x1 equals f. And then I have m2 x2 double dot plus k2 x2 minus k2 x1 is equals to 0. This is third and this is fourth. Okay, and if I write in matrix form, I will basically end up with this system. M1 0 0 M2 x1 double dot x2 double dot, which is time derivative, plus x1 x2 0 f, and this is k1 minus k2. Then you have k2, and here you have negative k2, and then you have k2. Is it making sense, guys? So far?
Yeah. Follow it.
Okay. And okay. There is one.
Professor.
Yeah.
You just rewrote equation 2 into 3, correct, and 1 into 4.
Yeah, but I put these in the left hand side. So here I basically took one, there is one mistake here on the signs, it is negative and this is positive. So this is K1 plus K2 and this is negative. So K1 plus K2, negative K2, negative K2 and K2. This matrix is a stiffness matrix. This is a mass matrix. This is
Professor?
stiffness matrix, yes?
Just quick question. You derive equation 1 as negative K2. Is this the a negative stand for the compression?
Yeah, so basically when you are actually displacing this mass M2 in the forward direction, what it is, the spring force will be restoring force, which will try to oppose the motion, right? So that it will be opposing the motion in the opposite direction. So mass M2 has been displaced a bit. So imagine that mass M2 has moved a bit. And because of that, this is basically experiencing a spring force in the negative direction.
Oh, okay. Okay. Yeah, just not too sure. Yeah, thank you.
Yeah, okay. So this is what we actually got. Now this is basically a second order differential equation. Second order differential equation. And to solve that.
Professor, I think your force vector kind of option FV on the top.
Yeah, you are right. Thank you. This F has to be on the top and this has to be the same. Yeah. So what we are actually getting, the second order linear system of differential equations. So basically we have one equation and there are two second order differential equations. Now what you have guys studied so far, or what we have studied, is we can solve a single second order differential equation if we are given something like x double dot is equals to, or x double dot plus, let's say, c1x plus C2 is equals to 0, then you probably know how to solve this system of equation where x is just one variable, single variable. But now what we are having is, we can basically solve that using, this is second order ODE. Second order ODE, and the solution for that is basically If you remember from your 501 class, you can basically find the lambdas, and that lambda 1 and lambda 2, basically lambda 1 and lambda 2, where lambda 1s are not eigenvalues here, but it will be just like substituting x is equals to e lambda t as a solution in this equation. You will end up with a solution which has the two roots of lambdas, which will be minus c1 plus minus b square minus 4ac divided by 2. And depending on that, depending on the property of these values, you will get different solutions. So if lambda 1, so let me actually write that case 1. If lambda 1 and lambda 2 are real and distinct, then the solution basically is a e lambda 1 t plus, let's say a1 a2 e lambda 2 t. This is one solution where a1 and a2 are the unknown constants which will be obtained using the initial conditions. Similarly, if you have case 2, if lambda 1 is equals to lambda 2, then x of t would be a1 plus a2 t times e lambda t. And case 3 is that if they are complex conjugate of each other, they are complex numbers. If lambda 1 and lambda 2 are imaginary, that is lambda 1 2 is equals to sigma plus minus j omega, then your x of t is e sigma t, then a1 cosine omega t plus a2 sine omega t, where a1 and a2 are constants. I mean, these are basically, I just tried to refresh our memories about solving a second order ODE which has got constant coefficients. So you have got second order ODE with constant coefficients C1 and C2 are constants. And this is again a homogeneous equation. So if you substitute x is equals to e lambda t as a solution in this equation, you end up with a quadratic equation in lambdas, and you solve that, you will actually end up with this solution. And depending on the different cases of lambda, whether they are real and distinct or same or imaginary, you can basically get the solution. And the solutions are, if you see, they involve two constants in each one of them. So in each of the cases, there are basically two constants, a1 and a2, unknown constants, that needs to be determined using the initial values. So initial values basically mean that what initial values you need is that what is the value of x of 0 and what is the value of x dot of 0. I mean, velocity and initial position. So let's say this is, let's start with 0 initial conditions. So these are the initial conditions that are required to solve for a1 and a2 in any of these cases. Let me know if you guys are getting what I'm trying to say. Are you guys with me so far?
Yeah.
Everybody is with me so far? Yeah.
Yes.
Okay. So this is when x is one single variable. But now what you see here, when we are actually looking at this equation, I do not have this equation which is only in x2. I have x1 term as well. Similarly, I don't have this equation only in x1. If I have all this equation in only x1 variable, then it basically resembles this equation for which we know how to solve. But here, because in this first equation, x along with x1 variable, the x2 variable also comes into picture. So it becomes difficult to solve using this formulation. So what we do, we are basically going to use the things that we have learned so far. What we have learned, we are going to diagonalize the matrices. What do I mean by diagonalize? So what I'm going to do is I'm going to rewrite this equation. Let me call this equation as 5. And I am going to write that as x1 double dot x2 double dot.
So Professor,
Yeah,
so we're not going to be using that approach then?
this one.
Yeah.
Yeah, we are going to use this, but for using this, we need these equations to be independent of the other variables. So this equation, if it has involves a double derivative of x1, it should not involve involve x2. Similarly, the second equation, if it involves double derivative of x2, it should not involve x1. So these are basically coming because of these values. These off diagonal terms, these are called coupling terms. They couple the variables in each equation. These are called coupling terms. They couple the equation together. Couple the equation together means they actually join the two equations together. The two equations are not independent of the other variable. Do you see what I'm saying? Somehow imagine that if this becomes 0, then my first equation will not involve anything related with x2. I won't have anything related to x2. Do you see what I'm saying?
Yes.
So that is what we actually try to do is try to somehow convert these off diagonal terms to 0. But to do that, there has to be some process. So we are basically going through that process right now. So what we are doing is we are rewriting this equation number 5 as so can I write my equation like this? The top equation like this. So what I did, I take this stiffness matrix. Oh, I need to have x1 and x2 here as well. X1 and x2. So I took this term, move it here, and then multiplied with the inverse of this matrix on the right hand side. So it basically becomes this matrix, right? So I will basically call the multiplication of this as A matrix times X plus, let's say F, let's say capital F, FT. So basically I got this formulation. Is everybody with me so far?
Yes.
Where your A matrix is, let me write down what is A matrix. A matrix is M1, 0, 0, M2, inverse times negative of K1 plus K2, negative K2, negative K2, and K2. That is your A matrix, which is multiplication of this with this. Why negative here? Because this matrix, this term will go in the right hand side, it becomes negative. And plus F0 will remain as it is, the vector will remain as it is. So this whole matrix A will be this, M inverse negative of the stiffness, and that times X. And your Ft will be, vector would be written as M1, 0, 0, M2 inverse times F0. Let me know if it makes sense, guys, or if you have any questions, let me know. Are you guys with me?
Yes, with you.
Any questions so far? If not, then we will take this equation and I will write it in another sheet of paper. But so far you actually know that this is the equation we have finally got. So what we actually
Can you go back to that page? I just needed to finish writing that bottom part.
Okay, no issues. Let me know if you have any questions, guys.
Got it. Thank you.
Okay, thanks. So this is what we actually got. Now, what we are doing here is just look at this matrix A. Now, A is basically going to be a matrix, which is 2 by 2 matrix, because A's matrix is obtained by multiplication of this with this. So this is multiplication. This negative basically means this negative actually multiplies with all the other elements on here. So it is not M minus this, it is multiplication is happening. This matrix gets multiplied with this. So this is a 2 by 2 matrix. So if this matrix A is diagonalizable, diagonalizable means you find the eigenvalues. I mean, step 1, find the eigenvalues. And that will lead to either two cases. A is diagonalizable, diagonalizable, and A is defective. Basically means when I find the eigenvalues and it is a 2 by 2 matrix, then either lambda1 and lambda2 are distinct eigenvalues. These lambdas are now eigenvalues. So these are eigenvalues. Eigenvalues are distinct. In that case, what we will get is an eigenvector. Solve for eigenvectors. That will be step 2. Solve for eigenvectors. And that will be V1 and V2. Construct matrix P given by V1 and V2. That is step 3. Construct P. If A is defective, then I know lambda1 will be equals to lambda2 because I have geometric multiplicity of lambda is less than algebraic multiplicity less than equals to. If it is less than, then we actually solve for the eigenvectors. Just like we have been doing so far, we actually solve for the eigenvectors. And in that case, you actually end up with V1 and V1 missing. I mean, one available and one missing. Step 4 would be construct Q matrix, which will be comprised of V1 and V1 missing. Let me know, guys, if you are with me so far or not. Are you guys following what I'm trying to do? Or you are not following? If you're not following, please ask. I will try to explain again what I'm doing.
Yeah, could you explain it again, please?
Okay, so let me then go back to the discussion we had at the very beginning. So very beginning when I said that I have a matrix A, and matrix A, I found the eigenvalues, and for those eigenvalues, I found the eigenvectors. Now, if I have repeated eigenvalues, then there are higher chances that these are not linearly independent and cannot be solved using this equation. I may need to use this additional equation to solve for the missing vector. So in any case, I have to find these 3 eigenvectors. So if there is a missing eigenvector, then I will get matrix Q. If they are not missing eigenvectors, all 3 are independent of each other, I will get matrix P. That's what we actually said. So that is what I wrote here in the last page. So in the last page, I wrote the same thing. So I first found this first system of equation using my physical system. I rewrite my matrix. And then I used this specific matrix A and found the eigenvalues of this matrix A. And then I saw that whether either A is defective, that means I have 2 eigenvalues which are equal to each other, or it is diagonalizable. Diagonalizable means they are distinct. If they are distinct, I found the eigenvectors and construct matrix P. If they are not distinct, I found the missing and then construct Q. Okay. Are you guys with me so far?
Yes.
Now, sorry, come again. Is there somebody who is having some question or doubt? Is everybody with me so far?
Yes.
Great. Okay, so, and we also have seen that after we got this matrix P, if I multiply this, we use this equation we actually got in diagonalizable form, or if I use this Q matrix and multiply Q inverse AQ, I got this matrix. So we have seen that, or we have not seen this specific case, but we have seen this specific case, and you can easily verify that if you have distinct eigenvalues, you will actually get this case as well. So this is, we basically have built a framework to solve this equation, which is coupled second order ODE. So we have built this framework, the groundwork we have did. Now how to solve that? We'll go to the solution. Now what the solution is, let X equals P times Y. Now P is a matrix which you actually got using this. After you found the eigenvalues of A, you get the eigenvectors and you arrange them in column format, you get P. So if it is diagonalizable, then you get X equals to Py. So let me start with this case first. So I will select X equals to Py and substitute in this equation. So what I will get Py double dot plus A Py plus Ft. Everybody's with me so far?
Yeah.
Yeah. And now I take P in the right hand side, then whatever I will do, it will be Y double dot is equals to P inverse A Py plus P inverse Ft. Is everybody with me so far? Yeah. I multiply P inverse on both sides. So this will become identity matrix. So this will go, it is just I, and P inverse AP, and then P inverse is multiplied with this as well, fourth term, P inverse Ft. Everybody is with me?
Yeah, I follow.
Yeah. And then what is this thing? This thing is nothing but we have seen it is just a diagonal form. It will, let's say, call that as D, diagonal form. So what we got as Y double dot as dy plus P inverse Ft. Now this equation is your uncoupled second order ODE. Uncoupled second order OD. Why it is uncoupled? Because now in my matrix A, this matrix is having all the off diagonal terms 0. This I will basically get that. So if I rewrite this equation, what I will get here is y1 double dot, y2 double dot is equals to, actually let me, so y1 double dot, y2 double dot is lambda 1, 0, 0, lambda 2, y1, y2, and let's say this after multiplication of this basically becomes G1t and G2t. This is just a force vector, a modified force vector. Now, if you look at this equation and you rewrite in the equation that in the simple, separate the equation separately, or write the equation separately, you will get as y1 double dot as lambda 1 y1 plus G1t. And the second equation would be y2 double dot is equals to lambda 2 y2 plus G2t. So this is, what's the last equation number we used? Number 6. So this is number 7 and number 8. Actually, let me write this as 7, 8, 9, and 10. And if you look at this is exactly the same form as we were discussing a while ago. I was discussing a while ago about how to solve a second order ODE using for constant coefficients. Remember guys?
Yeah, I recall.
Is everybody following what I'm trying to say? I said that if I have a second order ordinary differential equation in one variable, I know how to solve this. This is a solution methodology. If somebody who has not taken 501, they can basically look at it and you can confirm that that is how it is being solved. If you have already taken 501, you probably have gone through this. So basically, if you have a second order ordinary differential equation in one variable, you can solve it. But here you have the two equations, second order equations, but they are also coupled. They are not individual in single variable. So what we actually did, we did um, some technique which we use to diagonalize this matrix A. And by diagonalizing it, what we actually did, we substitute x is equals to py. P matrix is obtained by these eigenvectors of the matrix A. So py, and then when we do this, we actually saw that we got a diagonalized form, and then each individual equation now can be solved as we have seen so far. Let me know if you guys are following it or not, or if you have any questions.
I have a quick question, Professor. So when we have a problem like this, can we
Yeah.
just construct the diagonal matrix without having to go through and find the eigenvectors? Because once we find the eigenvalues, we can just construct the matrix, right?
Uh, you can, but then you cannot construct this matrix, this vector.
Oh, okay. Yeah. Okay.
Here you need P inverse FT because this will not be obtained without obtaining P.
Oh, okay. Yeah. Thank you.
Welcome. Any other question, guys? So with this, there are other initial conditions also that are there. X0 is, let's say, X naught, and X dot 0 is, let's say, X dot 0. So basically the initial conditions will also change when we are solving this. So initial conditions will be X0, instead of X0, it will be P Y0 will be X naught, and Py dot 0 will be X dot 0. So Y of 0 will be P inverse X0, and Y dot 0 is going to be P inverse X dot 0, X naught, X dot naught. So these are the initial conditions that will be required to solve for these set of equations 9 and 10, because 9 and 10 are individual second order ODEs. So you will require initial conditions, because we have seen for second order ODEs, it involves solutions which have two constants which will needs to be determined, and these initial conditions will be used to determine that. Once you have got Y1 and Y2 separately, then what you can do, you can go back to this substitution. You can go back here, and let's say once Y1 and Y2 are solved, then X can be obtained by P times P matrix times Y1 and Y2 simply. So you will get X1T and X2T. X1T is basically the displacement of mass 1, and X2T is a displacement of mass 2. So this specific technique is called as modal decomposition. So we call this technique as modal decomposition technique. Modal decomposition basically means you find the eigenvectors, which are also called as modes, and you use them to diagonalize a matrix. Okay. Just go through this and just take few seconds to look at that and let me know if you have any questions. Okay, guys, any questions? Should F be in the top row? That's what probably it's a while ago, right? If I'm not making a mistake. Okay, so any questions, guys, so far?
Professor, so
Yeah.
this is for the A's diagonal case, right?
Yeah, so this is basically we have seen for the case where our A was diagonalizable. Diagonalizable means we have substitute X is equals to Py. In case A is defective, defective means I cannot have distinct eigenvalues. I mean, there are repeated eigenvalues. For 2 by 2 case, lambda 1 and lambda, there are only two eigenvalues. That's why I said lambda 1 equals lambda 2. If it is A is 3 by 3, we have lambda 1, just like we have seen, we may have lambda 1 equals to lambda 2 and lambda 3 may be separate. So depending on how many eigenvalues are there, but if it is a defective, then there is one repeated eigenvalue. And for that, there are chances that you have the geometric multiplicity is less than that algebraic multiplicity. That means I cannot find independent eigenvector. Then I have to use that equation to find the missing eigenvector, and I have to construct Q. And then instead of x equals to py, I will take x equals q of y if your A is defective. Everything else will remain same. So instead of P, substitute with Q. Everything will remain same. The only thing that will happen is now you will not get lambda 1, lambda 2, 0, 0. You will get lambda 1, 1, and 0. You will have 1 here instead of zeros. So we will see, or you can actually verify that even in that scenario, you have one equation which is independent of the other variable. So for example, I take this equation or this set of equation and say, let's say A is defective. Then what I would have got using x equals q of y, I will get y1, y2 double dot equals lambda 1, 1, 0, lambda 1. That is in Jordan form because we know that Q inverse AQ will be in a Jordan form. It will be a J matrix, Jordan form matrix, where lambdas will be in the diagonal form, and there will be one, number 1 will be in the super diagonal position, times y1, y2 plus, now let's call this as h1t and h2t, where h1 and h2t is basically, instead of P inverse, it is Q inverse. So h1 and h2t are Q inverse f of t. So here, if you look at this equation, if I write the equations back again, I will get y1 double dot is equals to lambda 1 y1 plus y2 plus h1t. That will be your number 11 equation. So this is number 11 equation, and y2 double dot would be lambda 1 y2 plus h2t. Are you guys with me? Are you guys with me?
Yes, Professor.
Yeah. So if you see, it is not an exact diagonal form where you have uncoupled equation. That is, this equation does not have any y2, is bereft or is devoid of any y2 variable. This equation does not have any y1 variable. So these are uncoupled equations. So you can solve independently, each one of them independently. Here, the first equation does have y2 term, so it is still uncoupled or still coupled. But if you look at the second equation, this equation is all in y2 only variable. There is no y1 variable. So you can solve this first for y2 independently. Solve this first for y2 independently, and then use that solution of y2 in this equation to solve for y1 independently, and then substitute y2 in this equation to solve for y1 independently. Let me know if it makes sense to you guys.
Professor, I think would be easier to like just solve through the example with numbers, because like I think like general equations kind of like still hard to understand without any numbers.
So the textbook is basically doing the same thing for you. So you can read the textbook. I'm just taking the same example. So I'm just showing you the steps. If you read that example that I was telling you, 9.15, it is exactly doing that. So let me actually give you a homework that, well, it is not a submission homework, but you basically read example 9.15 and you will basically learn and appreciate the process we are doing here.
Professor, on the left side, it says inverse of Q times A times Q equal what's a J matrix?
J, Jordan matrix.
Oh, okay. Yeah.
And going forward, it will be, there will be, say, there will be some times when I will be using just generic variables, and there will be times when I will be using numbers. So it will be hard for me to repeat everything with the other process. So if I would have started with the numbers, then it would be hard to show it using the variables. And if I started with variable, then it is hard to show it using numbers, because that means I have to take another lecture to do all the steps again. So that is the reason, once I have taken one path or one process, it becomes difficult to move to the next. I hope you understand my dilemma here. Are you guys following what I'm trying to say?
Yes.
Yeah, I get where you're coming from.
Yeah, so please do not take it otherwise that I'm not doing it using numbers. But the thing is, once I started taking some steps, it becomes very hard to again go back and do it using numbers, and then it becomes very difficult to show you, because it will take another lecture, nothing else. But let me know if something you are not following it. I will try to explain again so that you are clear, or if you are missing anything, I will make it.
Sir, I have a question.
Go ahead.
So let's say we have an eigenvalue that's repeated 3 times. So
Okay.
the equation that we have, we'll able to find. So we'll find one, and that will be considered available, and then we'll use that
Yes,
equation to
yes,
find the missing. But how do we
yes.
find the third one?
So just say that there are two missing ones, right? So you first find one missing, okay, using this as a V1 available. And for the second missing, you use this one that is already solved in the right-hand term.
Oh,
Say.
okay, okay. Yeah.
So once you have solved for this, this becomes your available now.
Got it. Yeah, thank you.
Then you use it here to find that. That's a good question. Any other questions, guys, so far? Okay, if not, then I will, I was basically hoping to complete this chapter today, but I believe we will take another lecture to go through the first order ODEs using this eigenvalue methods, or using this method that we have been learning so far, how to find the eigenvalues, how to construct matrix Q or matrix P, and then use them, or use this specific matrix multiplication to reduce the differential equations and solve them. So we have seen how to solve second order differential equations today. And the next lecture, we will see how can we solve it for nth order differential equation, any order differential equation. So we will use state space variables. We will use state space variables to reduce the nth order differential equation into first order ordinary differential equation, and then we will solve that using the solution methods you have learned in 501. So this is just to give you a heads up about the topic that we are going to cover in the next lecture. So probably if you find time, you can basically look at and refresh your concepts about first order ODE and so on and so forth. But the whole objective for today's session was that what we have seen that if you have a second order ODE, second order ordinary differential equations generally is very common in physical systems. So if you have a second order ordinary differential equation and you have a system of second order ordinary differential equations like this, then how can you use diagonalization concept to reduce it in a form where we know how to solve it? So if you can reduce the system of equation in this form, where each equation is consisting of only one variable. So if this equation consists of only x1 variable, or this equation consists of an x2 variable, it becomes easy to solve because we know how to solve for that scenario. So that is what we have covered in today's lecture. Any questions, guys, so far? So if not, then let's wrap up our discussion for today's class. And the next class, we will, as I said, we will actually go through state space system of equations, and we will solve, instead of second order, we will solve first order ordinary differential equations.